I'm very excited to introduce our keynote speaker for the open house, Ryan Groves. So Ryan earned his bachelor's in computer science at UCLA, and then he went on to do a master's in music technology at McGill. He's also been the director of R&D at Zaya, where he developed a musical messenger app called Ditty. You might have heard of it. It automatically sings your text messages. And this app actually won Best Music App for the Appy Awards of 2015. More recently, Ryan did a work on computational music theory, and he actually won Best Paper at the 2016 International Society for Music Information Retrieval Conference on that single author paper. And following that, he's now a co-founder of a company called Melodrive, and he's working with two co-founding PhDs to look at building an artificially intelligent composer and changing the way that music is generated and used in video games and also in virtual environments. So let's all welcome Ryan Groves.
So yeah, my name's Ryan Groves. I'm a co-founder at Melodrive. And there's no signal. So yeah, I want to talk to you today about building artificially intelligent musical composers. So I wanted to start off with some human composition. So what is musical composition? What do we consider composition to be? I wanted to pose a couple of questions and give you an example. So what are the goals and what are the outcomes of musical compositions? And how is it composed? Why do they use that word, compose? So this is an example of a very human process, which is an improvisation. So it's a real-time composition by a professional musician.
I would like to start with a free improvisation. And I decided a few minutes ago that I would do a Baroque improvisation on... But in this case, I will... Okay, so this will be the theme that I will use. After, I will ask you to give me themes.
Here she's processing. So that's an example of a human composition that's done sort of on the fly. But you can see that she's composing different elements together. So she said she's doing this in Baroque style. So at the beginning she establishes some sort of melodic embellishments that are typical of that style with little trills in the melody. She starts off with setting the key in the tonal center, so she actually doesn't give you the seed musical material until later in the piece. So she establishes that by doing sort of harmonic sequences that end in cadences. And she actually uses the same cadence twice in a row before she moves on to the musical material. And something that I noticed in your guys' experience of that piece is that you had an expectation of that seed material. And so she was sort of playing with your expectation by creating a prolongation at the beginning and then establishing that she is using that seed material. And so at that moment when she introduces the material, the audience reacts in the video and as well today. Some of you even laughed because you recognize that your expectation is being resolved. So music is more than just the collaboration of different components, but it's also it's about the listener's expectation and playing with their expectation and resolving expectation. And that's how sort of emotion is communicated through music. So how do we do this with artificial intelligence? I would argue that no one system is adequate. The problem's too vast to just apply one machine learning model and say, okay, I've solved it. So where I start is let's try to build a system that composes music that is similar to what humans compose. Because there's a huge challenge of evaluating these systems. It's a very subjective thing to compose music. What is a good composition? So if we aim to compose like humans compose, then at least there's some sort of metric that you can potentially evaluate on. So I've always used the analysis synthesis method. I've focused really a lot of my career on computational music theory. So I'm trying to analyze large data sets of musical pieces for their music theory components. And then with certain models, you can create generative models that you can turn around and then generate musical sequences in that style. So you can apply this method to different compositional devices. And you can also apply this method to sort of listener expectation. So there's some experiments there as well. So often it's not a truly artificial method, right? There's always going to be a human in the loop at some point, whether he composes the system that generates music of any style, or whether he composes, or whether the human actually hand tunes the features and creates some sort of logic in there. At a certain point, there's always going to be a human in the loop, even with these new methods that kind of do it themselves, so to speak. So the methodology that is used, that I subscribe to, is that you take an accurate measurement of something and then extrapolate that into a machine learning model, and that's where you get some really cool results. So I wanted to give a little music theoretical background. Schenkerian analysis was one of the most recent classical tonal music theories. And it happened, it was before computers were around. After computers were around, this generative theory of tonal music kind of came about, which starts playing with these psychological principles and integrating them with the musical analysis. So let me give you an example of Schenker. So Schenker thought that every single piece had this Ursatz, which was a fundamental background structure. So this, in the top right, this is the sort of fundamental one. So every song, he argued, goes from the third note in the piece and descends down to the tonic of the piece. And there's harmonic relationships for those particular notes in the piece. So it establishes the key on the tonic, and then goes to the dominant and returns to the tonic. And so he argues that every single piece has those elements in the background level. And you can reduce the surface level to get to that background level. So it's kind of an assumption there. So I wanted to give an example of that. So this piece has a incomplete double neighbor, which is this movement of da-na-na-na, and it happens right in this second measure. So yeah, see if you can pick it out. It's kind of slow. But. So when you do the Schenkerian analysis of this piece, what you realize is that he's actually using that same melodic figure in the middle ground and the background layers. So on a very abstract way, similar to how the human improviser that we saw earlier was using that very small musical seed material and pulling different musical elements from it. So she was using the da-da-da-da, and she just chose that small music unit and repeated it and transposed it and played with it so that we recognize that it was that piece. So that's kind of the same idea that Schenker had. This is what it means to be a composer, is to use these elements at different levels of abstraction in the piece. So the generative theory of tonal music used the principles of Gestalt theory. They really focused on, okay, what does it mean to have music grouped? So he took analogs from Gestalt psychology and vision. So in this case, if you have three items and the center item is closer to one side, perceptually you're going to group those two items together. And you have sort of gradients here of how much they're grouped, from grouped to not grouped. So what they said is, like, let's create a rule set that groups musical ideas in the same way. So the musical analog is time-based. So if two notes onset very close to each other and there's a third one very separate, then they're going to be considered to be grouped. And so what they did is they provided a huge set of grammatical-based rules for the systematic breakdown of musical structure. And their goal was to be able to implement this thing in a machine. People have been trying for quite some time. There's a lot of subjectivity to it, so it's quite difficult. But I think the real insight there was this grouping principle. So I also wanted to give you an example of sort of two different ends of the spectrum in terms of how much a human is doing. So these are two different compositional devices or facets of composition. So automatic orchestration and automatic expression, so performance expression. So in this case, this is sort of an expert-based system. So there's this theory called Z-chains by Siegler, Hendelman, and Donna. And what they did is they grouped notes based on the direction of the interval. And the group would extend until the direction changed, essentially. So up here you have this chain of up intervals. Here again you have one up before it changes direction. And then again you have 5 notes that has up. So these are sort of these up chains. Then they actually apply this hierarchically. So they look at the last note of all of these first layer chains, and they say, okay, actually these 3 chains are also moving in ascending fashion. So it's like an up-up chain. So they applied these two hierarchically, and what they were doing basically is discovering musical gestures in the piece. And so what they applied it to is automatic orchestration. So they found the set that covers the most chain, the chain that covers the most musical gestures in the piece, and assigned that to a particular instrument, and then redid it for the rest of the notes and kept assigning instruments until it was populated with a set of instruments that could perform that piece. So be kind, because it's all MIDI instruments with this example, but you get a pretty good idea. So you get a pretty good idea. It actually sounds relatively human. So this is kind of an example of a sort of a handmade system, but still using algorithmic techniques and sort of evaluating data sets of digital scores. So on the other hand, there was a model for expressive performance of piano pieces. So what they did was they formed basis functions for each of the dynamic notations in a piece. They first applied a simple regression, and they incorporated this model for melodic expectation and closure into this probabilistic regressive method. And then they did it again in 2016 with neural networks. And so what they're doing is evaluating a piece for all of the dynamic content. So here you have a basis function for piano, which is 1 when it is a piano dynamic and 0 when it's not. Same thing for forte. They have one for crescendos. So here you can see the dynamics are increasing gradually. They have one for accents. So these are kind of spike, like unit functions. And then they do it for sort of the metrical structure. So they're able to sum this up, and what they do is they measure the actual performance of the piece in terms of its dynamics, its loudness, and they relate that to their curve. So then they can go and generate the same kind of thing. So they did this with dynamics and with timing, and here's one of their results. So it's quite a good result. This was with the bidirectional recurrent nonlinear basis model for reference. So yeah, this is basically a neural net approach. So they took a bunch of performance data, they had these basis functions, and they created a mapping where they could generate them on a new piece. So another component of music is rhythm. So how do we generate rhythms? So there was a particular measure of rhythmic similarity proposed, which essentially relates inter-onset intervals. So if you just have the onset information, you can measure the distance between them. This was extended to polyphonic similarity. So you could basically, if you had something like a drum kit, which had toms, snare, bass drums, hi-hat, different instruments. So those are all monophonic rhythms that you can use this similarity metric on, and then you basically just sum them all together, and you create a measure of polyphonic rhythmic similarity. So using this, you can actually build a generative model. You can create a rhythmic space, and using some dimensional reduction techniques, you can create a map of similarity. So first, here's sort of the basic metric. What they found is with this inner onset measurement, you could actually group the perceived rhythms. So they tested it against people's perceptions of these rhythms and found that it clustered, essentially. So then, with the rhythm spaces, they applied this rhythmic similarity algorithm, used dimensionality reduction to get sort of a map of similarity. And you can see, again, this kind of clusters according to genre, as you might expect. So hip-hop is especially sort of clustered in one area, but I mean, with any sort of genre mapping space, you always get a lot of bleed over because there's a lot of borrowed content from genre to genre, depending on your genres. So once they have this rhythmic space, they're like, okay, so how do I define a point that is not in my data set? How do I click on this 2D space and generate one of these things? So they created a metric for interpolating on the right, interpolating between two rhythmic patterns. This is, again, using their monophonic similarity metric. So they actually have a tool, which is pretty cool. So this is a max patch. So you can actually interpolate between funk and house, for example. So let's hear all the way up to funk. So that's pretty funky. So you can start sliding to the right. And you can actually already tell that hi-hat is very house to me. So if you slide all the way over, all of a sudden you got a house beat. So it's pretty effective. So that's just one example of rhythm. So I've done a lot of work on setting lyrics to a melody. So with my work at Zaya, we built this automated musical messenger, and the goal is to set any text to a melody of your choice. So we have a limited catalog of melodies. But so immediately there's some challenges to overcome. Mainly when the text is too short and when the text is too long. So let's go into a sort of a regular example. So say you selected the song Can't Feel My Face by The Weeknd. The original text from the melody is 13 syllables long. The input text I gave it was 10 syllables, so it was do-wah-ditty, ditty-dum, ditty-do. So let's hear this awesome clip from the original. So, what does it sound like when we use custom text? So, it sounds natural, right? But there's kind of a lot of thought that goes into this, surprisingly. So you notice, actually, we use this technique, a vocal performance technique called melismas, which is when you extend a syllable over multiple notes and sort of create a smooth transition between notes. So see if you can pick them out from this melody. So there's actually 3 of them. The first 6 syllables has 2 of them, and then here at the end, there's another one. So the first 2 ones, they sound natural, but it would be very easy to make an unnatural sounding thing that also aligned these phrases. So it goes do-wah-ditty. You could also do something like do-wah-ditty, which all of a sudden is very unnatural to the human ear, but it's based on our understanding of rhythms. So because it's very syncopated, we think that's unnatural because that's just not what normally happens in music. So we had to create a model for mapping this sort of this metrical accent in melodies to accents in speech. So another example of text that's too short, we took a bit of a different strategy with this one. You just enter do-wah-ditty. This is what you get. Do-wah-ditty. So we just made short songs. But still, when it creates a problem, you have to decide, do I use the short song? And what if it was 2 more syllables long? Should I cram it into the short song, or should I double the text and add it to the long song? So you still have to make those decisions. So on the other end of the spectrum, what if your text is too long? So I gave kind of a challenge to this one. So I chose the song Habanera, and my text is, will you please set this text automatically? I'll use my extensive vocabulary. And in the app, we give kind of an indicator of like, we don't know if we can fit this text in this melody. So, but pay attention also to the phrasing of both the text and the melody in this case. So here's the example. So you can see, actually, it paused at exactly the correct moment. It completed the phrase, jammed all the text into that first phrase, paused like you would expect, and then moved on to the second phrase, because there were 2 melodic phrases in that particular example. So this app is mostly used for 2 things, which is comic relief, and people also try to do parodies. Parodies is a particularly challenging thing because when you have specific songs, everybody identifies with the sort of cadence of the text in that song. But if you're building a system that's supposed to handle everything, then you can't really have the artistic license that artists use. So part of their artistry is to create a unique text setting for their songs. So the comic relief also comes from sort of contrast between the emotional content of the music and the emotional content of your text. So here's an example. Some opera musician is rolling in their grave right now. And then here's an example of a parody. I had to be careful with this one, but here you go. Another one bites my butt. Another one bites my butt. And another one down, and another one down. Another one bites my butt. So I think the engineers knew a little more how this app was going to be used than the executives. So it would have been a bit of a surprise for them. So let's move on to another compositional device, harmony generation. So hidden Markov models were used pretty extensively in speech recognition to identify phonemes in spoken audio, and then also to identify words from those phonemes. And actually, it applies really well to music. So Microsoft invested some research time into this, where they would identify the pitch content of a particular measure of audio, and they would align the tempo so they knew it was a measure, and then they would create a hidden state layer of chords. So the chords would actually, based on what pitch content was in the audio, you would sort of have distributions for which chord it might be. And then similarly, there's transitions between chords. So there's probabilities for all these transitions. So here's an example of that.
At first goodbye, she got on a plane, never to return again, always in my heart. Ba-da-ba, this love has taken its toll on me. She said goodbye too many times before.
And here is the chord progression that they discovered, and they used band in a box to create the accompaniment.
At first goodbye, she got on a plane, never to return again, always in my heart. Ba-da-ba, this love has taken its toll on me. She said goodbye too many times before.
So pretty good. So they basically just trained it on a ton of songs that were annotated with chords, did the analysis of those vocal parts, created the probabilistic distributions, and then you can generate chord progressions for new audio material. So I've tried this technique myself. So let me just show you this. This is kind of the diagram. So the observations are what you see, and so once you train it, sorry that the contrast is not great, but once you train it, you can take new observations and generate this hidden layer. So the hidden layer in that situation was this sequence of chords. So what you can also do is, what I experimented with is you can say that, okay, maybe a state will dwell for a particular amount of time, a particular number of observations. So in this case, there's multiple notes, and a chord can sustain over multiple notes. And what that lets you do is it actually decides the transitions, not only what chord it's going to be, but when they transition. So let me play that example for you. So this is the input melody. I tried to enter some chromatic material in there, just to see what it would do, essentially. And this is the chord progression. So it's not bad. It kind of loses focus there a little at the end, but you can see this was trained on a rock and roll data set, so it kind of it has that rock and roll effect. Part of that is the production that I personally did, but still it's a viable solution in this case. So similarly with melody, I've done a lot of work on melodic analysis, and I've also borrowed some natural language processing techniques. So context-free grammar is a formal grammar where you have rules of ways you can expand certain symbols. So you have non-terminals and terminals. I'll give you a specific example so it's a little more accessible. But on top of that, you can create them in a probabilistic way by sampling a data set. So I use these grammars to apply them to music, to melodies, by sampling pitch intervals. So in the case of grammars, here's a couple of example grammar rules. This is a noun phrase that gets expanded into a determiner and a noun. The determiner can be expanded into the word the or a, and a noun can be expanded into the word dog. So immediately when you see the tokens the dog lined up next to each other, you know that this noun phrase rule will apply to it. Similarly with something like the park, if you had another rule that where a noun can be expanded into the word park, then you can start building this grammatical structure from a sequential input. So in this case, you see a verb phrase up here, so there's a verb followed by a noun phrase. This is a prepositional phrase, which is a preposition followed by a noun phrase. So it gives an idea of what function each of these tokens have in grammars. So I wanted to see if I could do this with melodies to find consistent relationships at different layers. And so this is kind of the Shankarian idea. It's like, can we apply the same rule at a different layer of abstraction to these melodies? And will that work? So I used it for melodic reduction. Because you're building this hierarchy from an input melody, you can actually start pruning the tree and create reductions. So the more important notes should be those notes that are represented in the higher levels of the tree. So in this case, this is Amazing Grace. And you can immediately see, so what I was trying to capture is these common melodic movements, like a passing tone, where you're stepping down by one scale degree twice in a row. And you can see that the tree actually picks that up sort of at the surface level. So it identifies that passing tone here. There's another one over here which relates to this passing tone. And so you can generate these trees automatically once you've trained it on a data set. And this is what it sounds like if you reduce the melody. So that's the original. So you can see it works pretty well, especially at the surface level. It starts making mistakes based on sort of metrical considerations, so it's not perfect, but it's a good approximation, and it kind of applies very generally. So with a model like this, you can actually generate melodies in the particular style that should be in the style of whatever your data set was. So it's a simple matter of sampling from this PCFG, and then you use the leaf tokens as a melodic sequence. So this is kind of a random walk sampling of that model. So you can see it kind of sounds like it's trying to compose something, but it's not really getting there. But there's also techniques. So this is just a random sampling. So you're going to get this sequence, or this tree that is generated to create this sequence is probably it's probably not the highest probability, the whole sequence. So there are ways of increasing the probabilities of your outputs, and there's kind of a sweet spot for having new content, but also having something that sounds good. So here's an example of melody generation with neural nets. So the other approach, really, which is let's just throw a neural net at it and see if it figures it out. So the neural net does the analysis, and with recurrent neural nets, you can apply it to sequential data. So this is from a researcher named Bob Sturm. I respect him a lot because he's very transparent about what he does. There's this whole concept of like, okay, what are we actually teaching these machines to do? And sometimes there's a lot of hand waving. So he trained this on 23,000 folk melodies, and this is what it's able to generate. pretty cool. The results are really nice. But even he says, okay, but if I seed it with something that's not in the style of an Irish jig, all of a sudden it can kind of explode and like fail miserably. So there's also, going sort of back to the repetition and structure idea, there's a lot of research in pattern recognition. I'm going to go a little more quickly through these because we're running out of time a bit. But basically there's algorithms for detecting boundaries in melodies. And this is the kind of thing you need to be able to do if you're creating an analytical generative system. So in this case, these are just an algorithm for finding repeated subsequences in the phrase, and you can use these boundaries as an indication of phrase boundaries. Similarly, there's another model that is more a perceptual model based on what they call the change rule. So he looks at a sequence of 2 intervals and measures the change in those intervals. So if you have a stepwise motion followed by a huge leap, that's a big change. So human listeners are going to perceive that to be a potential boundary. And it especially applies for duration. So if there's a really long note, you expect that a new phrase is going to start. So this is used in generative systems as well, in semiotics. So there's sort of a new methodology where people are saying, okay, maybe I can borrow some of the abstract features of an existing composition and generate into that sort of framework. So in this case, there was a study on transchord progressions, and basically what he's doing is assigning a variable to each of these chords. So this is an 8-chord sequence from left to right, top to bottom, and he's basically just bucketing each of these chords and assigning a certain variable to each of them. So then what he does is he finds the transitions between all the different chords, creates a probabilistic model, a very simple one, and then uses these variables as a template. So in this case, for example, this one, so the template is A, B, C, D, A, E, C, F. So the chord that happens at the very beginning of the first 4 chords should be the same as the first one in the second 4 chords. And it creates a really sort of human-like feel to it. So he used a sort of a trance production template, so it actually sounds like trance music. So you can see the repeated chords have to be exactly the same as what was generated already, and the new variables actually have to be new chords. So you can't repeat something that's a different variable. Similarly, there's evolutionary algorithms are used to use the musical material of interactive performer. I think I'm going to skip this one because we're running a little short on time, and I want to show this next one. Another way you can do it is with Markov constraints. So Francois Pachet and Sony CSL have done a ton of incredible work on using Markov constraints to generate music. And what he does is he uses constraints so he has a general model that's trained on a lot of data, and then when the performer is playing something, he uses constraints to reference the material that the performer is giving him. So you can see that it actually is referencing the material that it was given in a very cool way. So what's the conclusion from all of this? So building AI composers, it's not a one-size-fits-all approach. You can't just throw, 100 petabytes of audio data at a neural net and expect it to compose Beethoven. And I encourage you to be skeptical of systems that claim that they can. There's been a lot of news articles recently. It seems like it's a new kind of space race thing. Every week it's sort of the first generated AI composed music. And Sony CSL, like I said, they've done an incredible amount of really high quality research. However, they released this one album and they claimed it was the first ever entire song composed by artificial intelligence. So they sent this email to this sort of press release to the Izmir mailing list, the Music Information Retrieval Group, and there was like a slew of emails where they were like, so what do you mean by first ever? And also, you say the entire song was composed, yet it's a human singing and producing the song. So where's the human really in the compositional process, and where's the machine? So I think there's sort of a lot of buzz around this. So I encourage you to be skeptical, but I also encourage you to be open-minded, because a lot of people have a knee-jerk reaction saying, artificial intelligence devices and systems should not be creative. And I think there's a lot to explore there. And it doesn't mean that we're replacing humans by any means. I see it more as an extension of humans. So yeah, there's often a human in the loop, no matter what. And there's also a really interesting space in computational creativity. So what does it mean for computers to be creative? And I think there's a lot of opportunity there because of the way machines process information. It's fundamentally different to how we process it. So is there a way for a computer to really be creative, and what will that mean? And I think that's something that we need to be exploring, but I also would urge researchers to have sort of a grounded approach where you can evaluate the different systems that you're doing. So at Melodrive, we're building an artificially intelligent composer. So we're gearing it more towards the interactivity element. We want people to we want to extend humans' capabilities so that if a human cannot be there to improvise a song, you can still have new content that responds to your emotional, the emotional storyline of your game. So I wanted to present the first ever entire song composed by artificial intelligence by Melodrive. So this is a sample from our system. This is the medieval style. Thank you very much.
All right, we have about 5 minutes for questions, so if anyone wants to talk to Ryan. Julie?
What is your favorite music?
My favorite music, I very much like anything with a funky groove, pretty much. Stevie Wonder is probably one of my favorite artists, but I also like, the music I listen to the most is probably without anything with a groove that doesn't have any vocals, because I use that to do work as well, because I get distracted by strong melodies and stuff. But yeah, I would say Stevie Wonder kind of encapsulates like my favorite music.
Thank you.
There?
Is one type of music more difficult to train on than other forms of music? Like, do you find classical more easier to train on versus hip hop?
Yeah, I would say there's challenges with many different styles of music. So, I mean, just with the examples you gave, classical has a lot of digital scores that you can have access to. So one problem is data when you're trying to model styles. Having a huge data set of classical scores is a huge advantage. That's why sort of thought chorales are kind of the de facto machine learning, test. Hip hop, for example, has really sort of elusive harmonic transitions. It's not a very harmonic-centric style or genre, so you actually have to really focus on different elements like the rhythmic component of hip hop. So I think it's not that one is necessarily naturally harder than the other. It's just that you need to focus on different sort of parts of the composition process.
You and then you.
So I'm curious about production values and
Yeah.
automated production, because I mean, you've referenced it a couple times, and it seems like a problem that is, hip hop right there. So
Yeah.
where are you going with that?
Yeah, so I think that is a big problem, and to me that's one of the compositional, one of the processes in the pipeline of composition. The way we addressed it, we actually, before Ditty, we created this app that was an assistive composition app. And so the way we approached it was the challenging way, which is we created like a digital audio workstation in the cloud. And we actually were one of the first ones to put these professional virtual instruments in the cloud and created this automated mixing mastering pipeline. So I think there's a lot of research in that process as well. Like Lander, for example, is a startup that does automatic mastering. I think they just focus on mastering now. So if you have a mix and you're done with your song and you just want the final touches on it, you can upload it and it'll automatically master it for you for a fee. So there's a lot of research in the production side of things too.
Computational creativity is a very interesting field. Do you think does it have any kind of limitation on the types of music that it'll create, and then after, like, there's a limitation in the variety or types, or and do you think humans are more creative than machines, or machines gotta be much more creative?
Yeah, that's a good question. I think that computational creativity in machines, I think it's going to manifest in a very different way than humans expect or even want. I think that there's sort of an understanding or like an assumption that if a computer is creating something and you don't like the sound of it, then it's not creative, right? So I don't know. It's a tough question to answer succinctly, but I think there's a lot of room for exploration in that space, and I think you're going to have to enter that space with a very open mind as to what constitutes legitimate music.
So, like, if you're using like specific like neural network model, do you expect like only specific kind of like composition coming out of it? And if you like change, if you're just like using different kind of ordinance or different number of layers and all that, like does the composition just change? Like
yeah, I think so. It seems, well, so you need a lot of data is the problem with neural networks, more so than regular machine learning methods, like statistical methods. So to have a lot of data that is sort of homogeneous, like in the same style, like that's why the example I gave was folk music, for Irish folk music specifically. So if you want to compose in a particular style, you really have to have that stylized data set. To extend that to be able to build a neural net that composes in multiple styles, I think that is a real challenge because you can't really control it. It's possible that you could create a more complex layering network to make that happen, but I don't really know, to be honest.
Okay, let's take one more question from John Chowning.
I wonder if you've had a hostile professional reaction to your work, as happened to David Coate.
Like a negative reaction to the work, or?
Yeah.
These are hostile.
Hostile, yeah. I mean, after building the Ditty app, I don't think you can be very hostile towards your work. I think I've mostly just been like sort of disappointed most of the time. Like most of the time, like, you know, I spent a very long time doing this automated music theory work, and I was like, okay, this is it. I got a model that really identifies, you know, music theory elements, and then it's still frustrating to get to the point where you can generate something that you would actually like to listen to, because it's really focusing on one sort of compositional device. So I was really focusing on melody. So turns out there's a lot more to melody than just the interval representations between the notes. So harmony is a big failure in that model. Repetition is very, very difficult, kind of for all machine learning models. The repetitive structure, I think, is really where they fall down very often. So.
Okay.
That's very good. What's the longest, which is kind of the David code thing, what's the longest piece that you've generated that you, before it sort of breaks down?
I haven't really tried to generate long pieces, but yeah, I think your assumption is kind of correct that a lot of times you'll get very small sections that are really pleasing, and then the next section could sound disastrous, right?
Are you purposely avoiding that?
Yeah, I think there's different approaches. I think you have to address the repetition and structural component in isolation in order to really address that.
Okay, let's give Ryan Groves another round of applause.